Let's post this in my story, a couple Discords. And let's put a link. It says there's a stream. Here we go. Okay, let's see. Link. Paste. Pop this out. And let's put a link. It says there's a stream. Post that, bring this over here, send GPU mode Discord. Doesn't seem to want to upload, but here we go. So today we'll be solving puzzle 9, scalar version of flash attention. It says it uses 0 programs, which is I'm a little confused about, but we'll see. But basically we're going to look at block size B0 for our key query and value vectors and process it in B1 less than T elements at a time. Sequence length is T. This can be done in one loop using a similar trick from the last puzzle. So if we go over what we actually want to do, right? What is flash attention? We're going to have a series of several elements. Like this. Let's delete that. Let's maybe try to put these all in the same line. And we want to look at the tension between all of them. So we have we have a key matrix, query matrix, and a value matrix. For each of these elements, we're going to multiply it by k to get the key value, multiply it by q to get the query value, and then we're going to look at every pair of q and k. So if you look at our flash attention spec, you see we have a row vector times column vector. We're going to get a large grid of attention values, and then we're going to accumulate those attention values using softmax to help us know which pairs are the most important to add up in our activation, right? So right here, multiply each of them by k to get our keys. So maybe I'll put this here, right? Multiply each by q to get our queries. Then we're going to take both of these and multiply them together to get a grid, right? So we're going to have our queries and keys like this. It's going to be the square matrix, right? And each of these is going to correspond to a concrete value. I don't want to like actually type all of them. I don't know if there's a good way to do this, right? But you could kind of imagine it's going to correspond to several rows of values. Then we're going to do the softmax right here across what? For each row. And we're going to multiply this same sequence right here by v to get our values. And we're going to use those softmax values we get from each row to get the new value for each item, right? So I'm not sure how I should depict this, right? But you can sort of imagine this row might say add a little bit of this one. This row might say add a lot of this one. This column might say add a lot of this one, and so on. And we'll get a result for what our new first embedding should be, right? So maybe I'll pose it like this, right? I'll put it like this. Bring this over here, rotate it. And we'll sort of put in parentheses like this whole thing. It's going to get softmaxed. Oh, come on. Right here, this whole thing's going to get softmaxed in terms of each row, right? Like right here. And that'll sort of tell us how much each v vector should contribute to get to our final new slot of vectors, because we're kind of going from sequence of vectors to sequence of vectors, but we're doing this attention mechanism in between. So first thing, before we worry about any optimization, let's just see if we can implement it, right? I have q pointer, k pointer, v pointer, z pointer. The big thing here is that for large n, right? So in this case, we're looking at t. We're not going to be able to load this whole thing into memory. So we want to think about how to do it in blocks, right? So what we could do is we could look at, say, these two. I always forget which one's row, which one's column. Queries are the, keys are the, oh, I could just look at the reference, right? Look at the reference. Queries are the columns and keys are the rows, right? So query, key. We'll look at these two queries and these two keys and get this block out of it, and so on. In this case, it's telling us to do it B1 less than T elements at a time. So we would look at these two right here and then kind of move along in 2x2 blocks. And then we could fill out this whole thing without having to have the whole thing loaded in at memory at once. There's a problem though, which is that we need the whole thing to be able to know how much of each V should it contribute, right? I might need to think about this a little bit. Because similarly in the softmax, we might be able to do like an online softmax. But then how do we compensate for V? We need to think about it a bit, right? Well, I'm going to start loading stuff in. I'm going to start thinking about that, right? We'll do, let's see, we have N0, B0. Where's B1? The original description and notations are confusing. Change the correct version. So let's read that. Use zero programs. Block size B0 represents the batches of Q to process out of N0. Sequence length is T. Process at B1 less than T elements, KV, at a time for some B1. Oh, just choose a B1. Okay, I'll just choose like 4 or something. So, first we say B0 is so let's look at our keys, queries. This can be Q, K, and V should be matrices, I believe. I don't know what the hidden dimension is, right? Oh, I can see in the spec. Q is tensor by 200, K is tensor by 200, V is tensor by 200. Well, we already have the vectors. We don't even need to do the multiplication. We have this, and we have this. We don't even need to do this part, this part, this part. We just need to do this part and the aggregation to get our final sum. So we're going to say I offsets equals TL dot A range 0 to B0. And I mask is going to be TL dot A range. Let's see. Oh, and the scalar attention means we're only doing it on single numbers. We're not even doing it on vectors. We're just doing it on literally single numbers. Okay, I'm thinking too much of old. Pay attention to shapes, right? This is literally just a 200 long vector. There is no hidden dimension. That's why it wasn't provided. So in this case, our I mass should be I'm not even sure if I and J make sense here. I'm just call it offsets, right? Offsets is this, and mask it needs to be less than T. We don't want to go off the edge of this, right? Down here. Then we're going to say for block in TL dot range 0 T B1, but I need to just choose a B1, right? So let's do B1 equals TL dot const x per 4, and I'll put a B1 here. Now what do we do? Batches of Q to process out of N0. Let's look at this notation one more time. We have I'm gonna ask ChatGPT to render this. This is probably the worst tool, but whatever. I don't want to go on overleaf and log in, all that. Oh man. Let's see. No. Okay. Ooh. Wait, yes. Mm. Still a bit confused on this, right? We still want to use our block ID. Maybe they just mean that you're going to use axis 0. Whatever. I'm going to call this PID equals TL.program ID 0. Offsets is going to be this plus PID times B0. Then I have this block B1. So this is my Q offsets really, right? And my Q mask. Which means I should be able to load in my queries already. So let's say Q equals TL.load Q pointer plus Q offsets to Q pointer plus Q offsets, and we need to use a Q mask. So if I print this block, it should kind of come out to just like a small sequence of 200 elements. No, it should just be a small sequence of single scalars. A range is range, must be a power of 2. And it puts in B0 is 200. And look, this one has B0 and B1. These seem like actually just not coherent. I'm gonna check the Discord. Because what if I put this here, right? What if I put like this, and then I ran. Oh, I need to put it into Triton interpret mode. Right here I have this. Looks like it's what's intended. So maybe we do it over here. I want to check the GPU mode though first. See what they say for puzzle 9. In Triton puzzles, look for 9. Hmm. I think we could just choose arbitrary B. Still a little strange though, like, hold on. I want to see in the initial setup what this guy is doing, because it looks like he got it to run. B1 equals 32. Yeah, I think there's an inconsistency here between Triton Puzzles Lite and Triton Puzzles. We're going to really do it with no programs, which means no blocks, which also means that we're going to load all of Q0 at once. Not Q0, so we're going to load all the queries up in one big chunk. So let's see if this runs. A range must be a power of 2. TL.next. How do you type it? I don't really remember it right now. TL dot. top. There's a, it is called next power of 2, isn't it? What is it actually called? Maybe this older version of Triton doesn't have it. This is strange. A range's range must be a power of 2. This might just be like kind of broken. I'm gonna change the test. I'm gonna change it to be like 64 or something. It's just obviously something bugged here. Having them both be the same size doesn't make sense. In which case we should use the program ID. And this should be plus PID times B0, like that. And now we should see for different program IDs we load different sections. Yep, just like that. Alright. So now we have our Q block. We need to iterate through our KV. Right, so we're going to say for blocking this, we can get our K and V by saying KV offsets equals this, but we're going to do V1 in block because we're doing it sequentially, and our KV mask I'm gonna assume this is non-causal attention because it doesn't really say anything about applying a mask. There's no mask pointer. So we're just gonna say KV offsets is less than T. Then K block and our V block will just be our TL.loads, right? TL.load K pointer plus KV offsets, the KV mask, and same thing for the V block. And now we have our K and our V. Now we just need to do what? Now we could find our X by multiplying Q and K. One thing we should do here is we should expand our Q block because we're always going to have this anyway. We don't need to do it over and over and over. So I'm going to put that right here. And then same thing for the K block. Let's just expand it preemptively like this. I'm going to keep V the same for now. And X is just going to equal Q times K. Now we have a block of our attention matrix, or we should at least. This should be like a 2x2 looking thing. Come on. Let's see. Damn, this long. This is what I was talking about, it taking up a lot of memory. So we've got, yes, this very long 2x2 block. Basically we have our 64, it should be 64 by 4, which looks like it is. I could try making this smaller, right? Let's make this 2. And now it should be 2 by 4, which it is. Nice. So I'm going to pause that because that's annoying. And we're going to make the 64 again. Alright, now what do I do with this block? Now I need to do my softmax in sum, right? So I might actually put this V after because we don't need it till later. I'm not sure how I do this with one loop. I see how I do it with 2 with this, right? So let's borrow this again. Here I'd keep track of my max with B0 and my denominator of size B0. And what? We're going to take the same code again. We're going to say, we're going to do this update right here. We're going to do our online softmax just like this. And then we're going to do this loop once more. And this time we're going to do the logic from the second one right? Which was this right here. And instead of storing the softmax, what are we going to do? We're going to take this softmax value and we're going to store those contributions into the z pointer accumulating v, which means that initially the z pointer needs to have zeros in it. Right? Especially since we're accumulating scalars, we're literally just going to fill it with zeros. So I'm going to say tl.store z pointer plus offsets. Let's call this q offsets. With our q mask. And what are we going to put here? We're going to put a tl.zeros of length b0. So just like this. Then here, we're going to do this operation. We're going to say O block call von tl.sum of the v block, which we also should have expanded just like the k block. Times our softmax. Just like this. And let's call this z block actually. And we're going to store z block right here. Let's see if I'm thinking about this right. So, sort of a weird proposition. I need to make sure I actually am understanding it correctly. have my maximum, have my denominator. So what I want is each element of my softmax times each value added together. But if I'm doing the online softmax, I'm going to have to correct some of these values as well. But will it automatically resolve itself, right? Like, so if I have, I don't know, how would I type this? Let's say I have e to the x above 3 minus 2 times v1 plus x above 3 minus, oh, and the new one's 3 for v2. I need to correct this one, right? Well, let's just keep it like this, right? X above, let's call it 2 minus 3, and 1 minus 3 for v2, and then I add a new one, and I realize, oh, the new maximum is 4 or whatever, right? Now when I distribute over this, will it work? Can I just do the same trick for this? I think so. I think it'll distribute, right? When I multiply this by x above, let's say 3 minus 4, what do I get? I get x above 2 minus 3 times x above 3 minus 4 times v1 plus x above 1 minus 3 times x above 3 minus 4 times v2, which gives me x above 2 minus 4 times v1 plus x above 1 minus 4 times v2, which means it distributes it. So I can distribute this update. I can just keep that cumulative sum going. So I wonder if that means I could have done this one. I see the difference. So for this one, we needed the individual elements to save. That's why we needed 2 loops. For this one, we don't actually ever need the individual softmax elements because we're using them to aggregate our v values into our z. So we can aggregate in SRAM and never actually like realize the softmax values into our high bandwidth memory, our DRAM, right? So to achieve this, what I'm going to do is what? I'm still going to keep it like this, and then I'll make the change later, right? So basically what I want to do is, for the C block, I'm going to do this, right? And then I'll only do this denominator update at the end of the block. So what I'll do is I'll aggregate the values into their final form, and then I'll divide by the denominator at the end. And so the thing to worry about is that there might be numerical overflow if I do that. So what I could do instead is I could just keep track of the best denominator so far, and then multiply by the old denominator over the new denominator, and that should keep the values in a more reasonable range, right? So actually I'll do that. I'll say old denominator equals denominator, like this. Then I'll say denominator wait, what happened here? This needs to happen everywhere, actually. Yep. So let's try it like that. Let's get rid of some of this other logic. Make it less confusing for ourselves. I'm also going to put this here. X block is this. So I've gotten my maximum. I've done this to my old denominator. To my denominator, I mean. Update my denominator. Updated my max. I should keep track of my old denominator as well. And when I do this right here, so we're going to call this our correction term, right? I'm going to call this my correction. And I'm going to correct my denominator, and I'm going to correct my my z block, right? So I'm going to say z block times equals correction. And what I'll do up here is instead of storing this in memory, I'll only do it in SRAM. So we're going to initialize our z block in SRAM with zeros, aggregate, and only write to it back to high bandwidth memory, and then so our main program once we finish our aggregation. So I'm going to say z block equals, yeah, that's zeros like this. And then z block time equals denominator times equal correction. Make sure I keep track of my old denominator. So let's call this our max correction, actually, right? Because there's going to be two corrections. Max correction. And then we're going to have our, I don't know what I should call it, like whatever the update to our denominator was when we added our new term, we need to correct for what our past values were with that. So I might say like, I might just call it denominator correction. That's the most obvious thing to me right now. Right? Equals old denominator over the new one. And then what I want to do is I want to multiply whatever's already in my z block by that. And then oh, I might be doing some order operations trouble here, but I'll fix it in a second. Once I do that, I can add my my v block in, right? So I have my v block, and I want to do this with it, right? I want to say add in the sum of the v block times the times what? I want my softmax. So we're going to call this, what do we want to do here? I think they call it P. So this right here needs to look different, right? We need to save this. I'm gonna just call this my x vowels is this, right? Some of the x vowels goes into our denominator. Then we can do our denominator stuff. But then we need to use our x vowels over here, right? We need to say, we need our softmax, which is going to be our exp vowels over our denominator. We multiply by our softmax right here. And once we've done this for all the values, and we've aggregated it like this, we're going to write it into z. So we're going to say tl.store z pointer plus, should be the same offsets that we use for q, right? So I might get rid of this q offsets and just call it, well, let's call this qv offsets maybe. I mean qz. Just like this. And then we're going to say qz offsets and qz mask. And that should be it, but I need to check. Well, let's just try running it, but I seriously doubt it's going to work. Even without the typos, I'm saying I don't think it's going to work. Log2e is not defined. Steal it from the last one, right? Cannot make ship compatible 4 and 64. Let's see if I'm doing something wrong here. I have B1 is 4, and I have B0 is 64, so it might be that, but something else going on. This problem description is messing with me a bit. QZ mask. Just like this. Let's check this out. 256 by 1, 1 by 4. This should be a 256 by 4. Right. Yeah. Then what? What's going wrong? We have this maximum, we have this exp. I somehow doubt it's going wrong anywhere here. Maybe here? I bet you it's the soft max. Just wait on a sec though. Yep. No. Something else is going wrong. The maximum, I think, has to be going fine, right? That's going fine. That's going fine. The sum is breaking. Really? So this operation is going wrong. Why? Isn't that what we used before? Let's see what this says. 256 by 4, 256. Maybe I need to be expanding this, but why did it work before? I'm using max the same way, right? Yep. IJ is 2D, and max is 1D. Like, what if I printed this up here? One 32 1. 256 4 256. Let's just try expanding it. Let's make this A. Vector like that. Let's see what it says. Two 56 4 256. Let's do the same thing here. Not really sure why that's happening though. Need to examine it later, but I just want to see if I can get it working. Yeah, there we go. Looks like the whole loop is executing now. And I think what I'm doing wrong now is just the order of operations, right? For these corrections. So let's see if we can fix it. Let's try. I'm gonna put this line up here. Then let's try it. see how far the values are. 1 1 1 1 1 1 for all of them. Oh, I need to actually store the Z block here. See how far off they are now. I was storing the mask, storing a bunch of truths. Minus 0.001, minus 0.001463. How about here? Minus 0.0011, 2.853. Let's see what log base 2 of E is. Or like let's get rid of this for a second. Let's do right. So we don't encounter any rounding errors with that, but it might be problems with the division that I'm doing too, or it might just be incorrect. But let's try that first. 0.001, 0.0009. Yeah, this doesn't look right. We can make this correction factor one big thing, I think, honestly. Couldn't we? Or no? Right, what do we need to do here? There's going to be we need to correct each term's contribution. But then there's going to be a thing on the bottom which is like a sum with the old max. And we need to kind of distribute along there too. Oh, the max doesn't actually matter when we're doing the aggregation. Only the denominator does, and the specific values for our block. because it's going to cancel out. We can factor it out from the top and bottom, right? All right, so we're going to say old max equals max. We don't even need to do this. We do need to do this, but not here. We could say this part's fine. This part right here is fine. I'm going to put this down here. Yep, just like this. See what it says. See if this is going wrong somewhere very obviously. So like the max right now is these values. This is our max. This is our Q. K. V. And Z. Z plus QZ. Z block. Z mass. Oh, I think this has to be big. Because of how I did it, right? Let's make sure that wasn't the problem. Do I have Q in K transpose or something? Right? Here I have Q times K like this, and then I'm keeping the max of max x1. Let's make sure this is axis 1. Should be. Oh man. This one's challenging, but I also think the specification is just kind of poor and I'm having to make up a solution on the spot. Alright, let's see. Ooh, I am getting a different result now. Let's make sure all of these sums are on the right axes. Let's do that. Is this going to error out again? Yep. I want to see if this has an argument called axis. Like, what's the difference between TL.max and TL.maximum? I didn't even notice I used two different things there. I hope they're the same, but it might not be. We back. Let's do. Trying to see if this has the same signature or not. Okay, that makes sense. So I'm using maximum properly, but I don't know about max. Let's make sure we're using max properly as well. Like this. Let's see if this runs or not. We want to make sure we do this along the first axis. Not the first, the second. But that's what should be happening anyway. Hey. All right, let's bring this optimization back in. Nice. So what did we do? We loaded in our entire block of Q. We accumulated an SRAM by using online softmax and distributing across our running sums and running denominator term. We distributed correction terms, so we made sure to adjust the maximum correctly, like this, and we made sure to adjust our running sum so far, our running aggregation of the Z block with our denominator correction. Then we could just load our relevant V values, and then finally, once we'd aggregated all of our V values together with the attention values, we can write them to Z at the end of our sequential loop. So we're able to save a lot of loads and writes because we only did this initial load on Q. All the rest of this math, here, it's all going on in SRAM. We only have to load this K block in and our V block in. So we load the K block in so that we could get the relevant attention values with the QK multiplication. We load the relevant V values in so we get the actual values to aggregate in our sum. But we don't write until we've completed our aggregation, right? I'm going to take 5 and see if there's any way that I can improve this program, maybe by introducing an axis or something like that. I'm also going to compare it against some other solutions I see and see if there's anything I missed. But yeah, sounds good for now. All right, let's review some other solutions and see if there's any improvements we can make to the one I made so far, right? So first thing I want to look at is like, what did they do here? It looks kind of different. So you have a flash attention kernel. Looks like they did use a program. I like these variable names better than mine. It looks like they also made the trade-off I was talking about, right? So in mine, I kept track of the denominator, right? And I adjusted it on the fly. And I did this because I reasoned that it would keep the numerical error. It would decrease the likelihood of there being like an overflow or something. Let's say if we had like really large scalar values, but at the expense of like numerical error because we're introducing and some flops because we're introducing more multiplication and division operations, and you can lose some fidelity as you keep sort of like wiggling around in this range, right? But what they did instead was they added it all up and then divided by the denominator at the end. It looks like, right? That's what x plus sum is, right? And I think maybe we should try that because it would allow us to chunk up our approach for Q, right? So let's try that. I'm gonna do something a little bit different here. What I'm gonna do is I'm going to copy paste this code over. And I'm gonna do a different implementation here. And so that way I don't have to change a whole lot of code in this one. And it shows that I have a bit of versatility, right? This one is, instead of using 0 programs, it's going to use 1 program access in our launch grid. And it's going to do blocks along Q. And to compensate for that, it's going to compensate for that, it's going to keep track of the denominator at the end. Right. Otherwise, I don't think there's much else to do. Unless I'm really missing something, right? Because we iterate across K and V sequentially, meaning we can still complete our full aggregation and all of that without needing to have access to all the Q values at once. So we could take advantage of some parallelism here. So let's try that, because I'm going to feel a bit sad if we don't do a little bit of parallelism during GPU programming. So I'm going to keep this code I had here, but I'm going to paste this other code I have here. And I'm going to use the B1 they gave me. So what do we have here? Now we're going across Q in chunks, right? Let's see. I'm going to replace this static one large load with a bunch of parallel loads that we do in blocks. I don't know if there's anything else I need to change though. Oh, there is. Well, not until we get to our new implementation, right? So now, we keep track of our denominator, just like we were, and our max. But instead of keeping track of our z block, we're going to keep track of our we're going to keep track of our x vowels like this, right? And then just divide at the end. I think we could do that for this one too. I didn't even think about that, right? But can't we just... Oh, well, it's the same thing, right? So we're going to make the trade-off I talked about. We could also make that trade-off here without introducing parallelism, I guess is the point I was making, right? We can just add stuff up in our z block, and then finally at the end divide by the denominator. Then we don't have to do any of this correction, right? It's sort of just up to you. Like, you would want to profile each and see if it makes a significant difference or not, or if it was even a bottleneck in the first place. That was my choice for this one. Try a different choice for this one. So I will still call this just a z block, but at the end I'm going to say z block divide equal denominator, right? And then I'm going to get rid of all this stuff, right? So we're going to say let's just call this x or something, right? And then here we're going to put x. And then we're going to get rid of all this denominator stuff. Except for this, we want to keep that. Do we want to keep this? I think so. Yes. Like this, and then over here, do we need to make any changes? So we updated our max, we adjusted our denominator and all that. Let's just try it. Puzzle 9 is not going correctly. Oh, we still need to, right here, we still need to say our correction term, right? Is this. And then we need to apply this both to our z block. So I'm going to call this max correction, right? And we also need to say denominator times equals max correction, just like that. Why is this a red? Oh, because how did that get there? And let's try that again. I think it's still wrong, but we'll see. Yeah. I wonder if there's something here I'm forgetting or not. So this should be about 0.23, but it's really coming out to a completely different number, minus 0.427. Okay. Let's see. KV offsets. That looks right. N0 is not accessed. Hold on here. Are N0 and T different? No, they're not. They should be. So I don't think it's that. Full max. Full zeros. No, I'm sorry. Full minus infinities. 9 full zeros. C block full zeros. This is kind of the max so far. This is gonna have our sums. C block's gonna have our it's gonna have our it's gonna have our dot products in it. Oh, there is something here, which is no, that's fine. I'm iterating through each one here every time. KB offsets, KB mask, K block is this, V block is this, Q block times K blocks are X block. I'm going to take my maximums, correct here from my old maximum, multiply this in my C block, and in my denominator. These are my new numerator values. This is my new denominator value. My new V values. I need to do my dot product, which is this, and add once I have all my dot products, I need to scale them by denominator and store. Looks right. It's something really, I don't know if I understand it well enough. I am gonna look here a bit. Oh, do they have a mask? Where's the mask? I mean, this all looks really similar to what I have. Except for this. Oh, I see. Over here, I'm surprised that wasn't an issue as well, right? Some of this should be... How did this pass? This should result in a bunch of zeros, right? And then, that's gonna mess up the... Is it gonna mess stuff up? It's gonna mess up the exponent, yeah. Unless... Unless they were all negative. Yeah, basically this should have this term here. And this. I'm surprised I didn't cause an error before though. But like like that. See if this still runs. Invalid value encountered in subtract. And let's see if this fixes my existing code as well. Right, so over here. So I need to be a bit more cautious with my masks when I'm doing broadcasted operations. Still wrong. I wonder if it's so blatantly wrong now, though, right? Minus 0.4727. Minus 0.2. I do still wonder what's up with this. Got TL.max. Looks the same to me. Looks the same to me. We got this factor. Got our sum. This looks extremely similar. I'm not sure if I see something that's actually... What's the actual difference? What? Okay. Yep. 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 Less than T. New max. New max. TL that maximum fees. Yep. QKX. So XBAX. We have our correction factor. Our new x sum should be denominator times correction factor plus the sum of x belonging to x is 1. P pointer plus off j, sj, 1. It's like the only tangible difference I see, but like it's not a real difference. Yeah. I'm gonna try something real quick, which is to just see if that sample solution actually works, because if it doesn't, then I'm wasting my time. So we're gonna try that. See if this even works, right? Well, first of all, only comment on this part. Now paste this in. Save. See, does this even work? It doesn't. Yeah, that probably should have been the first thing I tested. Alright. Honestly, it seems like both of my sources kind of have a poor implementation for this, so I'm gonna kind of skip over this one. Maybe we in the test puzzle we can kind of just skip 10. Let's see. Run puzzles. I'm gonna comment this one out. And I'm gonna just paste the one from here that I did. And leave it at that. Leave a little comment maybe. Like that. Leave it at that. So I'm gonna put a little let's run and see that it skips us to 11. Oh no, it doesn't. Oh, I accidentally did it on 9. I should have done it on 10. So undo that. Do it over here. Try one more time. That looks more correct. No, it doesn't. Let me get rid of this print. Nice, I saw it go to 11. So I'm going to get a dot, git commit -m, puzzle 10, position and get push. Alright, if you're watching, thanks for watching.